Good evening, all.
Welcome to the live session for the course Matlab programming for numerical computation. Let's wait for like few more minutes so that more students can join and we'll start the session soon. So whoever is there in the meeting, please do stay here. We'll start the session soon. So let's begin the session. So last week we had discussed about solving ordinary differential equation. I hope you guys already remember what we discussed last class. So this week we are going to extend this topic. So last week what we did was we saw ordinary differential equation in single variable. So just a second. So that is you had a function in such a way that it was dx by dt was given as some function of x. So here the only unknown variable was x. So as a result, we saw several methods like the Rangakuta method, RK methods. We saw Hume's method and all those RK2, RK4, RK6 methods. And we also solved ODE solvers such as ODE 45. Okay. Now what do we get as a solution for this? So we solved initial value problems. That is at time t equal to 0, we know what the x value is. So let x be equal to xi. So this data is given to you. Then what do you get as an answer? We get x t versus x. So that is for different values of t, given that at t is equal to 0, xi is xi. For different values of t, we got how the values of x is. So that's what we got using the ODE solver so far. So far we had discussed about Euler's integrated and Rakakuta methods. We saw Matlab solvers such as ODE 45. There I also said that there are other solvers that is available like ODE 23s, ODE 15s, and also there are other solvers also. We'll look into that this week. And next we saw higher order Rangakuta method like Rangakuta fourth order, Rangakuta sixth order, all those methods. And we also saw error analysis. That is how is error changing with respect to your step size h, and we saw what is the global truncation error, local truncation error, and all those things. So this is what we saw in the previous week. Now here what we do is, here we did for single variable, right? We had did for single variable. Now we will be extending this concept of ODE into multivariable case. That is, you will have different, more than one unknowns, like x and y could be the unknown. So there will be some function like dx, it will be dx by dt. You will have some function which is a function of both x and y, and you will also have some function like dy by dt, which is also a function of x and y. So these two are coupled. Okay, you can't solve one alone and the other alone, because you can see here this y is there, and for this function x is there. So it is like coupled with each other. So we need to solve both this ODEs together. So now we have two unknown variables x and y. That is a multivariable case. And then we will be saving what is called as the stiff ODEs and non-stiff ODEs, and we will be solving some practical examples. Okay, so now let's start. In case you have any doubt in between, please do unmute yourself and ask, or else you can just put a message in the chat box. By the way, am I audible?
Yes, ma'am.
Okay, thank you. Yeah, so let's begin. So the multivariable ODE. So here you are seeing a system which is called as a damped spring mass system. So here you can see, here you have a mass M that is attached to the wall using a spring. So this is a classic example. Okay, this is the example that is usually solved in this numerical methods textbooks. So what happens is, here you have seeing a second order equation, that is you're seeing d square t by dt square. So it's a second order. It's not just dx by dt. It is a second derivative. So this is a second order equation. And here it is given, here the only unknown is x. Okay, so right now the problem is, earlier I said we are going to solve for multivariables, but here if you see in this equation, there is only one variable that is available. Okay, what does that mean? So what happens is, if you are given a second order ODE like this, okay, to solve this, first you have to convert a second order ODE into a first order ODE. That's the first step to do. Okay, that's the first step to do. And how do you do it? For doing that, what you have to do is, so here take this equation. Okay, so what we do is we initialize a new variable, and that new variable is in such a way that we say let dx by dt. Okay, so let dx by dt equal to v. Okay, this is a new variable that I declare. Now what happens? Now again I'm taking a derivative of this. So that is d square x by dt square is equal to dv by dt, right? Okay, so now we have got two equations. We assumed this, and from this equation you get the second equation, right? Now let us write this particular equation using our definitions here. So instead of m d square x by dt, you will have dv by dt, and plus c is a constant. And instead of dx by dt, you can write p, right? Plus k x is equal to 0. Did you get this equation? Now let us rearrange this equation in such a way that dv by dt will be on the one side and other terms will go to the other side. So that is minus cv plus kx divided by m. Okay, so now what happened is, you got two equations. This is one equation, dx by dt equal to v. This is second equation, dv by dt is equal to some function of k and v and x. Okay, so this is a first order ODE. This is first order. This is also first order. Now what happened is, we converted this second order into two first orders. Now you can solve this in such a way that you will solve for the multivariable ODE. Okay, so this is what we are trying to do here. So here you can see we have the first equation, dx by dt is equal to v. Okay, now if you substitute that into the previous equation, you will get this one. That is mv dx by dt plus cv plus kx is equal to 0. And you are also given initial condition. So the initial condition of the problem, it will be given like this: at t equal to 0, x is equal to 1, and dx by dt will be equal to 0. So this is the initial condition that is given. So in our case, it will be v at t equal to 0, x is equal to 1, and dx by dt we have told it is v, right? So v is equal to 0. So this is your initial condition. So that's what is given here. Just a second. So that's what is given here. At at t equal to 0, x is equal to 1. At t equal to 0, v is equal to 0. So what we do is, since we have two equations and two initial conditions, You would have seen this in the previous sessions also. What we do is we will tabulate all these functions in the form of a column vector. So what we do is we generate a first we need to create actually three columns. Okay, three column vectors, not three columns, three column vectors. Okay, first is of the variable column vector. Okay, okay. So the variable column vector I am calling it as y, and y is like this. Y, it is a column. The first value is the first unknown. So my first equation is this, right? So the first unknown is x. Okay, and the second equation is this. So it is v. Okay, this is first column vector. This is my first column vector. My second column vector is the function column vector. Okay, so that is this. So the function column vector, you will have this the right hand side of the equation. So that is first equation is v, and the second equation is if you bring it this everything to the other side, you will get minus cv plus kx divided by m. Okay, so minus cv plus kx divided by m. This is the second equation. So you got the variable column vector, you got the function column vector. Now it is the initial condition column vector. Okay, initial condition column vector. So what do? Your initial value is 1 and 0. You can just make it as a column vector like 1, 0. Okay, since you call this y, let me call this y0. Okay, so this is the first column vector. This is the second column vector. This is the third column vector. One for the variable, one for the function, and one for the initial conditions. Okay, so this is how you make it. So once you have made this column vector, what you can do is you can pass this on to a ODE solver. So I'll show you the syntax. So this is a function column vector that you see here, and this is the initial content column vector. So what you can do is the question is asked that solve it using an ODE 45 solver. Your unknowns m is given as 10, c is given as 5, and k is given as 15. And till t equal to 10 means your t span is 0 to 10. That is a question. Okay. And the similar question, we have to solve it using the RK4 method also. So let's try to do that. I'll share Matlab quickly. I hope you can see Matlab. So now, okay. So this is the function that we are writing for ODE 45. So ODE 45, if you remember the syntax, first what we have is we have a vector for the solving the solution, t solutions, and corresponding y values will be saved in this vector. You call the ODE 45 like this. You tell which are the variables we are looking for. So it is dy by dt. In our case, y is equal to x and v. Okay. So it is dy by dt. You're telling y and t is the variable. This is a function which will have the function, all the two functions. It is a function of both t and y. Okay. And this y will have x and v. Okay. This y will have x and v. The y is a vector. Now t span will be the 0 to 10 and y0 will be the initial condition. So this is y0. This is a column vector 1, 0. This is t span 0 to 10. Okay. So you declare the y0. You declare the t span. Okay. This is the syntax t solve and y solve ODE. You have saying the variables. This is a function. You give the t span, you give the y0. Now the important thing is to understand how the function is. So let us go to the function. So the function is named as mass spring fun. We'll go to the mass spring fun here. Sorry, not this. Okay. So mass spring fun will take in two variables, that is t and y, out of which you're telling that the first value of y, first entry of y is x. The second entry of y is v. Okay. And we have the constants. I think c was set to be 5, right? So let's just make this 5. Okay. C was 5, k is 15, m is 10 as per given in the problem. And this is the function. So fval is the column vector for the function. And you're telling that fval 1, 1. 1, 1 means first row, first column. That is v. And fl21 means second row, first column. So this is the second row and first column is this. So that is minus cv plus kx divided by m. Okay. You write this also as a column vector. So this is a column vector. Okay. And this fval will be given as the output here. Okay, so it is function f(val). You're taking in the time and the y, and the y you are extracting x and v. You write the two functions with the variables we have, and you output the function. So this is the syntax. So now what we do is you go back to the ODE solver. It calls in this function. So first let us just run this, okay? And then I am commenting this out right now. First, let us see what is happening when we run this. So you can see the answers in t-solve and y-solve. So t-solve, so this is your initial condition. Okay, initial it is 0 and 1. 1 is for x, this is for v. Now this is your t-solve. That is from time t equal to 0, ODE 45 will take its own time step, and it will be till what time? It will be till 10, 0 to 10 you have. And corresponding y-solve, if you see, y-solve will have, so t-solve has 85 entries. So y-solve will also have 85 entries corresponding to every time, and it will have two columns. What does this mean? First column, if you see, the starting value is 1. See, this is the initial condition of x, right? And this is the initial condition of v, if you remember it. Okay, so the first column corresponds to the first variable. The second column corresponds to the second variable. So what happens is, if you want to plot this, okay, if you want to plot this, what you'll do is, okay, let me just write this one. I'm just plotting t-solve versus y-solve. And remember, y-solve has two columns. Okay, so when I run this, I get I get two lines. One is corresponding to x, other is corresponding to y. As you remember, x starts from 1. Okay, so this is the line corresponding to x. This corresponds to x, the position, and this corresponds to dx by dt, that is a velocity. And as you can see, x starts from 1 and y starts from 0. Okay, it's an oscillatory behavior for the spring mass system. Now what you can do is, if you just want to plot one of the data, not all the solutions, if you just want to plot the for example, let us plot just the position or the velocity. Okay, here the code is being given for the velocity. What do? You plot the t-solve, and in the y-solve, you only extract the entries for the velocity. That is the all rows and second column. The first column is for position, the second column is for velocity. So you extract the solutions, all rows, second column, you will get the velocity. So velocity alone, if you plot, you will be getting like this. I'll just comment this out. You will be getting just the velocity. This is the velocity versus time. Any questions in this?
Ma'am, in the assignment question, they asked particularly to find out x value at one like that. How to find out that, ma'am? What is a command for that?
X value for the particular time. Is it like that?
Yeah.
Okay.
Yes, ma'am. Yes.
So for that, I had, what we will do is, you can see here, you are given T-span. Okay. So T-span, I've done it for 0 to 10. So that is why in the T-solve, you will see these many times. Okay. So
Okay.
instead of that, if you want a particular time, what do you do? For example, I just want it at 5. Okay. I want to know exactly what the value is at 5 seconds. Okay. So what do I do is, in the T-span, I add that. Okay.
Okay.
And it has to be in the proper order. This has to be the initial, this has to be the last T. And this in between, the time should come in between. Okay. So now I'll run this. Let me just clear all. Okay. I'll run this. Now if you see, my T-solve only has 0, 5, 10. And my Y-solve only has 3 values. This is corresponding to 0. This is corresponding to t equal to 5. And this is corresponding to t equal to 10. So if you
Okay.
want a particular time, what you can do is just add it in the t-span, and this will be the graph. This is for time t equal to 0. This is for t equal to 5, and this is for t equal to 10. You can just add it in the t-span. You'll get the exact value. Okay.
Okay.
So now the next question is, okay, I'll just show you how the system behaves with a different value of k. different values of C. So here you saw an oscillatory behavior for the mass spring system. If the C is like increased, let us do it. Okay, I'll just plot this one, not the whole solution, just this one. Okay, you are getting an unstable behavior. Okay, so C equal to 5 is an ideal value for the system. Uh, okay, now going back. So that's the physics part. Okay, even if you don't understand it, that is fine. Okay, now we have to do the same thing using the RK4 method. So RK4 code, we have already seen it in the previous class. Now we have to see how to code RK4 if we have multiple ODEs. That is ODEs in multiple variables. So what do you do is, we go to the previous RK4 method, this RK4 code. This code is the same thing that we wrote in the previous class. Okay, we have to just note where we have to make the changes. So here, let us go one by one. Just a second. So here first is, so the first you say at t equal to 0, your y value is 1 comma 0. You have to, initially it was just single variable. Initially you used to just write y equal to 0. Now it is a vector. So you write 1, 0. So this is your initial value. Next, t end is still 5. H, let us keep 0 0.1. And n remains as such. How do you calculate n? N is nothing but tn minus t0 minus divided by h. N is calculated. Now what you have to do is, you have to write the time vector. So the time vector starts from t0 to tn with a step size of h, like we used to do it earlier, and it is a column vector. So that is why you can see this symbol here. It is a column vector. Now what you do is, earlier what we did is, before starting the loop, we used to initialize y to be zeros. Okay, the y value we used to initialize all zeros. How many zeros will be there? Okay, it will be the size of the t basically, or else you can write zeros. Usually we'll write zeros like this, zeros, like to, so it is basically 1 rows and n plus 1 entries will be there. So n intervals means n plus entries will be there. Earlier we used to write like this. So it was just a row with all zeros. Not row, actually it's column, right? 1 row and n column. So sorry, it's not like this. So it used to be y, initially it is used to be like this, column vector 0, 0, 0, 0. It used to be like this. Okay, just 1 row. Yeah. So now what we do is, here we are declaring zeros to be 2 rows and n plus 1. Okay, just a second. This column and row that you can like change. Okay, it doesn't have to be a column vector or row vector. It's only that this calculation has to be corresponding to that. So here what you have did is, here it is 2 rows and n plus 1 columns. So here what happens is 2 rows. Okay, 2 rows we are declaring it to be zeros. Why is it that? The first row corresponds to the x variable and the second row corresponds to the v variable. So here we have 2 rows instead of 1 row. Okay, otherwise in the previous code you could have just 1 row of values. Okay, you need not have this. This row is also completely fine. Okay, so here we have 2 rows and all zeros. Now what we do is, out of that, the first column, so this is what all columns, all rows, first column, right? So that we are declaring it to be y0. So now how does the entry look like? It looks like 1, 0, and rest all will be zeros. It look like that. Okay, this is how this will look like, capital Y so far. Now what we have is, we are coming into the loop. So for the loop, what we do is, you start the loop from 1 to n intervals. Your first value of y is, it is the first column. Okay, take the first column. So earlier it was 1, 0, 0, 0, 0, 0, 0, 0, and so on. First, you will take this column. Okay, so that is what is happening here. And for this particular entry, we'll calculate what is this mass spring at the following k. We will calculate what is the k values. Okay, for the k values, what do? You have to just input this one for the mass spring fund, which is already written. So here the mass spring fund we have, it will take the t value and the y value. T value you can see that is ti, which we used to do earlier also. It used to be just ti. And y value here, you can see that this is a vector. Okay, your yi is a vector. And spring fund, from that yi vector, it will extract x and v. You don't have to worry about it. It will be extracted here. And you will calculate what's the spring fund here. So as you know, earlier K1 used to be just one function. It used to be a scalar value. Now what happens? K1 is also a vector like this. It's a column vector. Okay, so this will have the function for x and this will have the function for v. Okay, not the x and v, it will have the functions, two functions. So here we will have K1, K2, K3 and K4. This will be a column vector, this will be a column vector, this will be a column vector. And when you add this column vector, what happens? Corresponding columns will only get added up. Corresponding rows will get added up. So you have K1 here as a column vector. For example, let it be AB. K2 has a column vector CD. Okay. When you do K1 plus K2, what happens? You will be getting A plus C and B plus D. So the corresponding rows will get added up. You don't have to worry about it. So this is the formula h by 6 k1 plus 2 k2 plus 2 k3 plus k4. This is a formula for RK4 method plus yi. You get the new y new. And what is this new y new? This is for the next time step. So that is y all rows. The next column I plus 1 means the next column is the new value. So likewise, you start from the first column, you go to the second column, from the second column value, go to the third column and so on. Okay, you start from the starting time to the end time. Now what happens is, okay, so now what happens is you need to find I'll just run the section by section, just a second. Okay, you can see y0 is a column vector. Now let us initialize. So initializing, you can see T is just a column vector with all the values from 0 to 10. Sorry, from 0 to 10. Now what we do is we'll see what the y values look like. So y value, this is what I said. Initially it is 1, 0. Rest all the entries are zeros. Okay. Now after that, we'll solve this. We'll run this section. Okay. I think I just ran it twice. Just a second. I'll run it once again. Run. Run. Okay. This is our y new. Sorry, y new is the last value. Okay, your capital Y is getting updated, right? So capital Y. Initial value is 1, 0. Now you can see the zeros. Other zeros has been updated. Now what happens? This is the X behavior. This is the next row is how the Y behaves. Okay. This corresponds to X and this corresponds to V. Okay. This will give you how X is churning with respect to time. This gives you X versus T. And this gives you V versus T behavior. The two rows. Now to plot this, what should we do? For plotting this, if you want the end solution at t equal to 10, if you want the end solution, what do? You extract all rows, the last column. Now, if you want to plot both the functions, you have to just plot it like this. You'll be getting both the plots, the same plot that we got using ODE 45. This is x changing from 1, it will go down, and this is the y value from 0, it goes up. Okay, just a second, this was for 50, right? Let's do it for 5 so that we'll get that oscillator behavior. Okay, we got the oscillator behavior, x value oscillating, and this is y value oscillating. Okay, now if you want to just plot one function, what do? You have to take t, the first column. If you just want the position, you take y, the first row, all the columns. So this will be just giving you the positions, okay, locations. I'll just uncomment this off. Okay, this gives you the position alone. Is this clear? Any doubts?
No, ma'am, no doubts.
Okay, so let's move forward to the next question. So the next part. So next discussion is about stiff systems and non-stiff systems. So stiff systems is, so if you take, we have two equations, okay? We have dx1 by d, so we have two variables. Earlier it was x and v. Here the two variables are, okay, here the two variables are x1 and x2. Okay, if you want, you can, so let's see how this function behaves. Okay, dx1 by dt, how does that function behaves? So that function, we'll see it separately. Okay, so what we do is, so this can be solved as independently because it is not a function of x2. And you know that the initial value at t equal to 0, x1 is 1. And this system also you can solve independently because there is no x1 here. And you can see when t equal to 0, x2 is equal to 1. So let us go to the ODE solvers and try to solve this separately. Just a second. Yeah. So this is a first ODE. That is, I'm getting t solve and y solve the solution. I'm calling ODE 45. I'm telling t and x is the variable, and this is the function. Since it's a very simple function, I'm writing it here directly. It is minus 100x. My t span is from 0 to 1, and at time t equal to 0, my initial value is 1. So instead of giving a variable, since it's a simple equation, I'm just directly writing what is the initial value. So now I'll just run this section. Okay. This is how my function looks like. So it started from 1. Initial value of my x1 is 1. So it started from 1. But as you can see, before even reaching time 0.1, this function has reached a convergence. It has reached a saturation. So this function had a quick dip. And after 0, so after this some point 0.05 or something, okay, after this time, this function is hardly changing. So after this time, you can see this function has reached a saturation. So this function is actually quickly changing function. So let's keep that in mind. X1 is, it is very fast drop. Let's keep that in mind. Now what we do is, okay, now what we do is we'll have the same method, but instead here now the function is minus 0.01x. For the same span and the same initial guess, let's run this section. Okay, you can see the time 0.1 is here. You can see the time 0.1 is here, but the function is still changing. So actually for the system, time 0 to 1 is not enough to actually capture what are the behavior of the system is. So what we do is, we'll increase the time span. So here I've increased the time span, the same function, but the time span is right now from 0 to 1000. So let me run this section right now. And this is how the function behaves. So now earlier x1 had a fast drop. It dropped before 0.1 time. But here you can see the drop is very slow and it gradually drops after around like 550. Some at around like 550 seconds, it reaches a saturation. Okay. So x1 is fastly changing function or fast drop and x2 is having slow drop. Okay. Now imagine you're solving this together. When you solve this together, what happens is this is having a faster dynamics and this is having a slower dynamics. Such system, okay, such system when you have multiple ODEs and one variable is changing fastly with respect to time and other function is changing slowly with respect to time. When there is a difference in dynamics, such systems are called as a stiff system. Okay. For solving stiff system, we have like a different set of ODEs so that you can identify. So it is called as ODE 15S. Okay, this S corresponds to stiff system. Like that, you have ODE 23S. There are several other ODEs. If you just Google it, you will be able to see several other ODEs. This S means it is mainly used for solving stiff systems. So we'll see what is the problem for solving this using the usual ODE 45 we have learned so far. So for that, what do we do is, so let us take these two systems together. For that, I have written a function multi-var fund. I'll open this. So the multi-var fund will take t and y. Out of the y, the first is x1 and second variable is x2. Okay. For simple functions, I'm just writing a matrix like this. That is minus 100. So A will look like this. A is a diagonal matrix with minus 100 and minus 0.01. And I multiply that with y. What will happen? So this is minus 100, 0, 0, minus 0.01, and that is multiplied with my function, that is y, which is having x1 and x2. Y is a column vector, right? So what will happen when I do matrix multiplication? I'll get 100 x1. This is 0. This multiplication is 0. This multiplication is 0. And this multiplication is minus 0.01 x2. Basically, I'll get the I'll get the function column vector. Is this clear? Okay. So that is the output that I have. This is the output that I have. I output this here. Now what I do is I run it for, sorry, I run it for 0 to 200 seconds. T-span, you can change it, it's your ish. And both my x1 and x2 initial value is 1. Okay, so now I'll run this section. Okay. So now you can see what happened. Your x1 is dropping very fast, but my x2 is very, very slow and it is still dropping. For time span 0 to 200. Now, if you look at how many steps it has taken uh, 24,157 steps. And if you look at the T-sol, you can see it started from 0, then you had e raised to minus 0.4. Actually, the step size between each time step is very, very less. Why is that? Do you know? That is because for this system, that is because for this system, if you have to study this system, you have to take very, very small time step. Why? Because for a very small time step, this function is changing rapidly. So this requires slow time step, slow time step to actually see what is happening in the system. But for this, we can take even larger steps because even if you take 0 to 20, the drop is only this much. It is slowly changing, right? So this requires large time step. But when you try to solve it together, one different dynamics, when you try to solve it together, because of this slow time step requirement, what will happen is the MATLAB will take small time steps. That is why you can see T solve, the difference is very, very small. Okay, so that is why it requires a lot of time. ODE 45 requires a lot of time to solve this. But the same thing if you run it with ODE, the same thing. Okay, the only thing is here instead of ODE 45, I'm writing ODE 15s. That is the only syntax difference. I'll run this here. So just note this number. That is 24157. Okay, I'll run the section, and here the output is in the variable T2 and V2 Y2. I'll run the section here. You get the same solution, but you can see it only took 88 steps. Okay, OD 15s took only 18 steps. But if you look at why it is, because initially it took very, very small time step because your first one function is very, very fast. Okay, so it requires small time steps to capture what is happening exactly inside that. But once that small function once this function reached saturation, what happened is it started taking big, big time steps. See here you can see the time step difference is very, very high from 11 to 18, from 18 to 25. Okay, say 92 to 112 and 172 to 192. The time steps is larger. So that is what the ODE for ODE 15 years, ODE 23 years. So what happens is this solvers initially it will take very, very small time steps so that one of the functions stabilizes. After that, automatically MATLAB will increase the step size. Okay, so that is why it is used for solving stiff systems. It is more adaptable for such systems. Okay, any doubts so far? So let us look at the theory. So ODE 45 is an explicit solver. It is based on Ragakuta method. So the time step is fixed. But here, okay, I have a question. Okay, no, okay, fine. ODE 15 years is an implicit solver. That is, it can vary the time step as per the dynamics of the equation. Now, this system is a system which has two kinds of dynamics. One is a fast dynamic and one is slow dynamics. Stiff problems can be more difficult to solve numerically because traditional numerical methods may require very small time steps to achieve a stable and accurate solution. In contrast, for non-stiff system can often be solved using large time steps with good accuracy. And so now is ill-conditioned metrics. That is, if you are given a question like this, how do you understand this question? Such a function is ill-conditioned, like such a function is a stiff system or not. So for that, if the equation is as simple as this, okay, if the equations are as simple as this, you can calculate. You have a matrix, right? You can calculate a matrix like this. Just a second. Yeah. If the system is very simple like this, you can calculate the eigenvectors of this equation. So this equation looks like this: minus 100 x1. Sorry, x1 is not there. Just a second. So this is minus 100, 0, 0, minus 0.01. And here you have function x1, x2. Okay, this is when you can write the function in the form of This is when you can write the function in the form of ax is equal to b. If you can write this in the form and a is the matrix, this is the matrix you have to find the eigenvalues of the matrix. Okay. So I'm not worried about the signs here, but just take the ratio of this eigenvalues. Okay. You have to take ratio of the eigenvalues. So this is the largest, let the eigenvalue be E1 and E2. Out of that, the maximum, let this be the highest value. Okay. So E1 divided by E2. Okay. So this eigenvalue ratio will give you an idea. If this ratio is very, very high, it means your system is a stiff system. If the ratio is very small, it means your system is okay. You can even work with ODE 45. So ill-conditioned matrix, it is a large ratio between eigenvalues. That is what is called as ill-conditioned matrix. Okay. So ill-conditioned matrix are stiff systems. Those can be only solved using. So for example, here if you see, you know what is the A matrix is. Okay. This is your A matrix. I'm taking the eigenvalues. Eigenvalues are 100 and so if you want to see what is the ratio of the eigenvalues in Matlab, there is something called as a condition number. You can directly calculate using that function, which is CONDA. Okay, CONDA, what it does is it takes a ratio of the absolute value of the largest eigenvalue and the smallest eigenvalue. So 100 divided by 0.01, it gives you 10,000. This is a very large condition number. So basically, large ratio, that means large condition number that is equal to ill-conditioned matrix and that is equal to a stiff system. And stiff system, you can solve it using ODE 15S, ODE 23S and so on. Okay, but this is only possible if your system is very simple and you can directly say or if it is a stiff system or not. If you have complicated equations, what you do is first try ODE 45. First try ODE 45. Look at how much time it is taking. If you feel that, okay, it is very, very slow, it is because the system is a stiff system, then you switch to ODE 15S. Okay, this is a standard procedure. First, every ODEs you try with ODE 45. If that is not working, then go to the other ODEs. Is this clear? Okay. Now let us go back to the next question. We have like another question like the same system, you have to solve it for a different matrix. So the matrix has been changed minus 5.7, 1.85, 13.2, minus 4.3. So what you have to do is you have already written a function. Here, instead of the A matrix, you can change the A matrix to this. So this is your A matrix. Okay. Let me just calculate the eigenvalue of this A matrix. Eigenvalue is this. Let's calculate condition number. Okay, condition number is very high. So probably it will not be solvable using ODE 55. Anyway, let us try. I'll just comment this because I don't want it to be printed every time. Okay. So I'll run it using this one. First, let me try with ODE 45. So I'll run this section. So you can see this is the solution that I get. Okay. Now let me see how many points I've taken. I've taken 2429 points. So let me solve the same thing using ODE 15. Yes. I get the same solution, but in like 40 steps. Okay. So this is much more faster. ODE, the 15S is much more faster because this system is a stiff system. Okay, here you can see that this 2429 is not a big number, but practically when you do such problems, if you find that ODE 45 is taking time, you have to stop it and then switch to the other ODEs. I hope it is clear. If you have any doubt, please do put it in the chat box or unmute yourself and ask. So the next question we have is the van der Waals oscillator. That is, we have an equation like this: x double dash minus mu 1 minus x square, x dash plus x is equal to 0. At t equal to 0, x is equal to 2 and x dash is equal to 0. So what you have to do first, you will have to write the equation. How do you write the equation? Let dx by dt or x dash be equal to y. Okay, let x dash be equal to y. Now what is d square x by dt square? That is x double dash. Okay, so we don't know that. So let's rearrange this. X double dash is equal to mu 1 minus x square x dash minus x, right? If I'm not wrong, this is equation, right? And here x dash we already know it is mu 1 minus x square. Instead of x dash I write y minus x. Okay, so this is the equation. This is my first equation. And this can be written as dy by dt, right? So this is my dy by dt. Okay, sorry. This is my one equation and this is my dx by dt. So dy by dt, dx by dt, I have function to be equal to y, and dy by dt, I have this function mu 1 minus x square y minus x. Okay, so this will give me the function column vector. My initial value vector is 2 0, right? This is the variable, this is the variable. X is 2, y is 0. So 2 0, and my variable looks like x comma y. Is this clear? Okay, now what we have to do is same system. Mu is a constant, so you solve it for mu is equal to 1. The same system, you change the mu constant to 100 and you have to run this. So yeah, let us go to Matlab. Okay, this is a system. So first let us solve for mu equal to 1. Okay, when mu equal to 1, this is the function that I'm giving it to the ODE. So this is whatever I have commented out, this is the function that you have to run. Just a second here. So what I do is I have t sol, y sol, I call ODE 45. My variable is t and y. My function is my db, dp, t and y. I will explain this later. My t span is from 0 to 10. My initial value is 2, 0. Okay. Now, what do we do? This is my VDP function. This is, it takes in t and y. From y, I have to extract t. For a question. And the condition number for previous is 1000 is less than the second one. My question is why the steps are higher for the first and the rather than the second. No, your number you can't decide based on the condition number. Okay, because if you have seen the if you have seen the first graph, okay, first graph it was like this. You had one function which is rapidly changing like this, and the second function it was changing like this. Okay, so the condition number it was smaller. The system behaves. It has to be based on the function. It is based on this function. Okay, 100x1. It is based on that. So based on that, the system is like this behavior is rapidly different. But if you look at the other system, one was like this. Okay, the other one was like this, something like this. It was different dynamics. But see, this is because of the similarity of these two function behaviors. So you can't just say by the condition number that one will take a larger step and the other will take a smaller step. You can't say it using a condition number. Just that using a condition number, you can say that okay, this system might be stiff and you have to reduce this. The number of time steps that is taken is completely dependent upon your ODE solver. It automatically selects it. Okay. One more thing I can say is that if you see this system, the second system, okay, it was like this, something like this, if I remember right. So let this time be 0.1. So what happened is your first your ODE solver, it took small time step from 0 to 0.1. After 0.1, it saw that this is stabilized, this is also stabilized. So from this, I can take larger step. Okay, but for the other function, what happened is, okay, this stabilized, but within that time period, you didn't have the other one stabilized. Okay, so that is that there is a difference in time steps will anyway happen. Okay, so this is not based on condition number. So I hope that is clear. Okay, so now from Y, if you have a further question, you can put it in the chat box again. Okay, it's fine. So now from Y, you extract X, you extract Y, you extract V. And instead what you do is, this is your first function and this is your second function. So in the derivation, I used y variable. Okay, here in the code, I'm using v as a variable. Okay, that's the only difference. M view 1 minus x square multiplied by v minus x. So this is also a column vector. This is taken as the output. So let me just run it using ODE 45 first. It takes 129 steps. Yeah, okay. Now what we do is, let me plot the solution. So this command I've already written. I'm just plotting x, okay, the just a position. This is how my system behaves. For mu equal to 1, you can see how oscillated the system is. Now what I do is, okay, ODE. Now the question they have asked us to increase the mu value, right? So for mu value, I'm making it as 100. I'm running it as using ODE 45, the same equation, okay? Now we can see it took 3485, okay? Now let me increase it even further. Let us look at the behavior also. So you can see when this behavior, the system has not reached a saturation, it is still decreasing. So let me just increase the time span. I'll just run it up to 100. Oh, it is taking a lot of time steps. Let me just plot it and see if the system is behaving. Okay, still it is not, still this time span is not enough. Yeah, okay, if you want, I can execute the same thing using ODE with 23s. Okay, instead of ODE 50 to 45, let me use ODE 23s. Same function, okay? It became 192. You saw the difference? Earlier, how much was the time? It was 23,777. Now the same thing when I used ODE 23s, it is getting in 192. And the plot looks the same. I can plot it and show you. The plot looks the same. Okay, but you can understand this 100 is also not enough. Let me just increase the time span. First, let me do it for ODE 45. I'm taking 1000 as a time span. Took 21,000, not 21,000. It is 2,81,000, 18,000, I think. Okay. Let us plot it. Okay, this is how the system behaves. Okay, now the same thing, let me run using ODE 23s. Okay, for 1000 time step. I'll run this. It got over in 2000 steps. And the plot will look exactly the same. See, the plot is the same. This is the plot. Okay, so this system, why it was taken an example, because for larger mu, it becomes, the system becomes a stiff system. Okay, so that is a property of this particular function. If you keep increasing the mu value, initially for mu equal to 1, the system was fine. Okay, you can solve it using ODE 15s or ODE 23s, it is fine. But as you increase your mu value, this system becomes a stiff system. So that is why you can see this drastic difference when you're using ODE 45s and ODE 23s or 15s, whatever it is. Is it clear? Okay. If no further questions, let me move on to the next section. So ODE 45 is the most preferred choice. If ODE 45 does not work, or if you know priorly that it may not work or your system is stiff system, then ODE 15s becomes the next solver of choice, or ODE 23s. ODE 45 uses the Rangakuta method. It is highly accurate for as a general purpose ODE. It is a very good solver. ODE 15s is a general purpose implicit ODE solver. These two will be sufficient for most of your calculations. There are other solvers also available, which you can just go search in Google. You'll be able to find it. So the next example that we'll be looking at is a stir tank heater. So the water is heated in a tank. It is continuously flows into at the room temperature. So you can see there is a water inlet and there is a water outlet. It comes in the room temperature, that is 25 degrees Celsius, and it gets heated up. There is a heat source here. Q is given as 500 rho Cp. Okay, you don't have to worry about this fire units. It's some heat is provided. So what happens? It is constantly stirred. So your 25 degrees Celsius water will be heated up and you get the heated water outside. So this is like the model of the water heater that is there in your bathrooms, which you use for taking shower. Okay, so this is how the heater works. So for that, here you have two ODEs. So this is a function of volume, dV by dt. Volume as a function of time, you have an equation here. And this is temperature with respect to time. dt by dt, you have two equations. And initial condition is at time t equal to 0, your volume is 1 probably 1 liter, and your temperature is 25 degrees Celsius. And you have all the other no, values given. Fn is a constant, 10 liters per minute, and alpha is also a constant, 1.6. Tn is 25 degrees Celsius. All these details have been given to you. Q value is also given to you. Q, I think it's 500 by, probably. I think this is 500. Oh, no, no, no. It's okay. It's 500 rho CP. So Q is given as 500 rho CP, right? So what happens is in the equation, when you substitute Q by V rho Cp, it is nothing but Q is 500 rho Cp divided by V rho Cp will come. So this will get cancelled. So this becomes just 500 by V, this part. Okay, this part becomes just 500 by V. We'll come to that when we are coding it. So let me share Matlab. So this is how the function looks like, which we are using for the ODE solver. It takes in a variable y. Y, if you remember, it will have two variables. The first variable is the volume. Second variable is the temperature. This is a constant f in 10, alpha 1.6, t in 25, q by rho cp. It is given as 500. This is the first equation. So first row, first column, f in minus alpha square root of v. Okay. This is the second row, first column. So it's a column vector. F in minus v, t in minus t. Okay. T in everything is given. So t is the unknown here. V is an unknown here. Q by rho cp. Basically, it will become 500 by v. Okay. This part will become 500 divided by v. Okay. Which we understood from the formula. Why is it so? Okay. So we have to run this. So for running this, we have written a script. You have to solve it for, so this is the initial condition. Volume is 1 liter, temperature is equal to 25 degrees Celsius. T span is for, let us do it for first 30 minutes or something, 0 to 30. I'm using ODE 45. T and Y is my variable. This is the function of my ODE functions. T span is from 0 to 30 and Y is 125. So let me run this and I'm plotting both. This is how that looks like. So my volume, sorry, volume is this. Volume started from 1 liter. It kept on increasing. And finally, after like 30 minutes, there was a constant volume of around 38.4511. And my initial temperature, it was 25. Okay. Because it kept on heating, the temperature got increased and finally it reached saturation. And my saturation output temperature is 74.99, right? 74.99 degrees Celsius. So my output from the heater, I'm getting a temperature of 74.99 degrees Celsius. And the constant volume that I'm getting as output is so this is what? This will be probably showing 26, right? Oh, sorry. This is 38 is the probably 38 liters or something like that. Is this clear? Any questions? If you want to know the last value, you can just take y solve and you can just print all the rows but the last column. Let me just look. Okay, let me just look at the shape. So it is rows and columns. So it is end, last row, all columns. Yeah, that is 34.41511 is the volume. That is the volume, and the 74.999 is the temperature as the last at the last 30th minute. Okay. So this is one example which we have seen in the beginning of our course. So we have the Indian captain Mahendra Singh Dhoni hitting a ball with an initial velocity of 35 meters per second at an angle of 45. So it's like a projectile motion. Okay. Now, if the boundary is set, so the boundary is set 75 meter from the batter, will the batter score a 6 or not? So when will it score a 6? If you know this ball is like a projectile motion, it will go like so. So the batter hits the ball and it goes from the ground in a projectile motion. So it goes from the ball in a projectile motion. Okay. So this is in the velocity. Sorry, I think. Yeah. Okay. So this, just a second. Okay. This is like 35 meter per second. Okay. At an angle of 45. Okay. Just a second. I think I'm making some problem. Okay. 35 meter per second at 45 degrees angle. Okay, there is some problem with my pen. Anyways, so what happens is when do you see that if the ball will go up initially and it will come down, right? So we have to check what distance it touches the ground. Okay, if touches the ground at before 75 meters, then it is not a six. If it touches the ground beyond 75 meters, if 75 meters here and the ball touches somewhere here, then it will be a sixer. So this is what you have to look at. You have, oh, sorry, I think there is a problem. Okay, yeah, I'm sorry with the pen. Anyways, so the acceleration, there are two kinds of acceleration. One is due to gravity and other is due to the air drag. Due to the air drag, you have acceleration in the x direction, and that is given as d square tx by dt square is given as minus ku, where u is nothing but the horizontal velocity. And that is given in the form v cos theta. Whatever theta is, it will be v cos theta. Next is this is the acceleration due to gravity, d square y by dt square. This happens in the vertical direction, and that is minus acceleration due to gravity, minus g. So initial condition is 35 meter per second. Initial velocity in the x direction is v net cos pi by 4. That is 35 cos pi by 4. And this is along y direction, the velocity initial starting is v net sin pi by 4. That is 35 sin pi by 4. Now what you have to do is, this is a second order equation. This is also a second order equation. This has to be converted into first order equation. That is how we solve it. So what we do is, I'll write one equation. Let dx, okay, let dx by dt equal to u. Okay. Next is, so dx by dt equal to u. Why is this happening? Yeah. Okay. So that is this here, whatever you are seeing it here. I'm telling dx by dt is equal to u and dy by dt is equal to v. Okay. Now what I do, I again take a derivative. So when I take a derivative here, this is what happens. If I take a derivative of this, I'll get this equation, right? So I'll get u dash is equal to minus ku. And if I take this equation, if I take a derivative of this part, v dash is equal to, that is d square y by dt square, this part. So then I'll get minus g. So this is my four equations here. So my vector will look like xv uv, xy uv, and my function will look like u v minus ku minus g. Okay, and my initial value, how it will look like, it's starting from the ground, right? So at starting, it will be 0, 0. For x and y, it will be 0. And then it will have u0. Okay, so it will be 0, 0, u0, and v0. Okay, sorry for that. It look like this. So this will be the initial vector. And this will be the function. This will be the variable. Any doubts? So let's try to plot that. Just a second. Okay, so this is a function we have. We have the initial velocity 35. My angle is 45 degrees Celsius. That is 45 degrees. So that is pi by 4. My initial position is 0. with respect to y direction also it is 0. This is my velocity in x direction static. This is my velocity in the y direction static. And I create a vector of the initial values that will be x0, y0, u0, v0. It will be a column vector. Now t span, I'm doing it for like 0 to 10 seconds. Now my ODE, I call, these are the variables. I call this function cricket fun, which will take t and y. Okay. And t span we have, initial values we have. Now let us look at this cricket fun. So this cricket fund looks like this. It takes in t, y, and some other variable which is called as param. So we'll see what is param here. I think I'm not transferring param here. Let me just see. I'll have to run this and see if this works. So t, y, and you have some other variable here. Now what happens is from y you have to extract the, sorry, this is not the function. This is the function, right? I was looking at the wrong function. So it takes t and y. The first variable is x, second variable is y, next variable is u, then next variable is v. Okay. Now what happens is these are the constant g, kappa 0.0.06, 0.006, and my function value is first function is u, second function is v, third function is minus kappa u, and the fourth function is minus g. This will be a four rows, one column. Okay, so that will be a single column vector that will go to this function. Okay, and now I am plotting multiple plots here. My first plot is t sol versus y sol. So basically, it will have four lines: one for x, one for y, one for u, one for v. So there will be four lines. And this what I'm doing is I am using t sol, and in the y solution I'm plotting all rows, but only first and second. First and second is what? First and second corresponds to x and y. So this will have only my position coordinates. In my second plots, I'll have both x and y with respect to time. Now in the second plot, what I am plotting is I am plotting the first solution, that is x. This is the second solution, that is y. So this is x versus y plot. So these are the three plots we have. Mm, just a second. Uh, So these are the plots we have. So this is the first plot. You can see how x is changing. So x is, it keeps on increasing. So horizontally, it goes on increasing from 0. Y, it is a vertical. So y, what is happening is, it is a red one. It goes high up in the air and it comes down to the floor. So if you can see, this minus 50, minus 100 and all doesn't make any sense for y. Okay, so once it reaches the ground, your height is 0. So beyond that, what happens? The ball, when it hits the ground, it will bounce back. Right, so that is not accounted here. So as long as it is touching 0, only till that the answer has a physical meaning. Okay, and you have your v and u velocities also changing. Now my second plot is for the location, that is both x and y coordinate with respect to time. You can see my x keeps on increasing, horizontally it is increasing, and my y, let me see where it is hitting 0. It is somewhere close to 5. Okay, so okay, if you see here at 5.04 seconds, my y is again coming back to 0. So basically within 5 seconds, the ball went up in the air and it came back to the ground. Okay, now let's see what's the time corresponding, what's the x value corresponding to this. Almost the x value is 122 meters. So that is higher than 75 meters. So basically this ball has went beyond the boundary. It has only touched the ground beyond the boundary. So it is a 6. So if you want to exactly look at the y sol, you can just go to the y sol here. And we are looking, the second column is y, right? So let us look at the point where second column has given, that is 50th entry. Okay, it is close to the 50th entry, and the t corresponding to the 50th t sol 50th entry is corresponding to 5.0429. Okay, corresponding to that many seconds, the ball has hit the ground. Any questions? Okay. If you don't have any questions, that is the last discussion of problems. Now we have like assignment questions, similar assignment questions to solve. So as we used to do earlier, I'll give you one question. I'll give you some time. Okay, do we have a question here? Ma'am, can you tell us what is the exam pattern for this particular course? So the exam pattern will be similar to your assignments. Okay, you'll be getting MCQs and such kind of questions. Okay, you'll be getting MCQs, you'll be getting match the followings. I don't think you will have access to Matlab during the exam. So you will have to write like small snippets of codes or something like that. Basically, you'll have questions like, is this the syntax to do this? So spot the error, or what are the functions that can be used for solving ODEs? Is Rangakuta, is how is ODE 45? Is an implicit method or explicit method? Like such questions will be there. Okay, and you can expect questions that are similar to your assignment questions. You can expect MCQs, match the following, fill in the blanks, and all those questions. So it will be a computer-based exam. I don't think you have access to Matlab. Where can I access these videos? So all the videos I upload it in the, just a second. Let me try to share it. Okay, just a second. Okay. I don't know if you can see this. So here in this, you have something called as problem solving sessions recordings. If you go click this link, you'll be able to see all my recordings and all the PPTs. The codes I'm not sharing with you. Okay. Codes you can just go through the video and then take a screenshot or whatever and try to solve the problem yourself. I'll not be sharing the codes, but both the recording of the video and the PPTs will be uploaded. But I hope that you attend the live session better than like accessing the videos. Videos you can use if you want to refer it later. But because in the live session, if you have doubts, you can ask me then and there. And I'll also have an idea of what your understanding is. So, so let's try to do today's
Ma'am,
problem.
I have one.
Yeah, question. Yeah, ask.
Ma'am,
Yeah,
if we can't able to access MATLAB means the questions will be very simple, right, ma'am? Because
yeah.
MATLAB is there means we have to solve the problems.
Yeah. So the thing is, I haven't got the guidelines of the exam so far. Probably it will be uploaded sometime in the website itself. So I don't know if you guys will have access to online MATLAB. So far, I don't have any information about that. Okay, but so the thing is,
Next week if possible.
yeah,
Please confirm next week if possible, ma'am.
yeah,
Because
okay, yeah, sure. See, you guys can also put a message. So there is like a Google chat that is available, right? In the So
I
that's a Q&A portion, right? So in the Q&A portion also you can put a question. I'll also try to inquire about it. Okay?
okay.
Yeah. Because I'm not a part of the team that is putting the question. So that is it. So this is problem solving. Let's begin with that. Uh, this is the first problem as we used to do in our previous classes. I'll just give you some time. Try to solve this problem. As you know, this is based on ODEs, so you have to just write a function for writing this part. Okay, rest everything ODE itself will do. So it will not take a lot of effort. So please open your MATLABs, or else you can use the online version of the MATLABs and try to solve this. And once you get the answer, please put it in the chat box. We'll discuss. Okay, even if you get the answers wrong, it is completely fine. But it is very important that you try to write codes. Otherwise, you'll not be able to learn this course. Okay. So I'll give you your time starts now. I'll give you some time. After that, we'll discuss. I'm getting answers. I want like more people to solve. Okay, I'll give you some more time and then we'll discuss. Do we need more time or shall I discuss the answers? So let's discuss the answer. So here we have like three variables, that is S, X, and P. Okay, so we have a continuous reactor which has like three changes, and X is the concentration of sugar, X is for biomass, and P is for the concentration of the pharmaceutical product. And you have given here other quantities like D is a constant, 4, Sn is given to you, R is a function of X and X, so you can write it, this R is relationship is given to you. Yx is a constant, Yp is a constant. So initially at t equal to 0, this is your initial guess, 5, 0 0.1, and 0. You have to use ODE 15s to solve the system of ODEs and find the concentration at t equal to 1 and t equal to 10. Okay, so basically you have to find, so t equal to 0 is given to you. Apart from that, you need to find a t equal to 1 and t equal to 10. There are some additional questions which I didn't show it to you, but yeah, but the whole thing is we have to find the concentration of these three components at time t equal to 1 and time t equal to 10. That's the question here. Okay. So let's try to solve this. Clear. CLC. And so this is the function. So first I'm writing all the constants here. So right now I'm just using, we have used the structures before. Okay, if you don't want to use structures, you can just pass on all these variables all of a sudden. Since I have a lot of variables to pass on, that is why I've written this as param is my structure's name. And in that I have the variable SI in equal to 5, D equal to 4, YCX is equal to 0.7, YCP is equal to 3. So when I run this, this is what I get. Okay, now I get what is param. If I type, I'll get like this. Param is a structure which has like 4 variables, S in D, YCX, and YCP, and each values are given. If I want to access any particular value in this, I have to write param dot sin. Then I'll get the value of it. Okay, so this is how you access the function in a structure. So now you have the initial condition 5, 0.10. I'm starting from t equal to 0. My t end, so basically my t span, what I want is, so if you look at my t-span here, I want 0, 1, 10. Okay. So this is similar to the question that I got from one of you. Okay. So my t-span I'll make whichever time I want. In the question, whichever time is given, I'll include that in my t-span. So I get 0, 1, and 10. So that is ODE 45. We'll look at the reactor fund. Just a second. Give me some time. Yeah. Reactor fund. So here what you can do is, instead of either passing this parameter, you can write this directly here also. You can just write Sn equal to this value, D equal to this value. That can also be done. Okay. Now what happens is, from Y, I'm taking in this X, I'm extracting X, X, P. Okay, this order is very, very important. I'm calculating R and I'm putting this in the equation. This is my first equation. This is my second equation. This is my third equation. Okay, this is how my function looks like. Now what we do is, we can my reactor fund T, Y, and I also send this parameter here, and T span is, which is 0, 1, 10, and my initial Y0 value. Okay. So whatever is required in the question, I am extracting that particular index. Okay. So we'll see that. But before, let me just clear CLC, run this. Okay. So this is how my values looks like. So my, okay, TS is from 0, 1, 10. And you know, this is my initial value for t equal to 0, 0, 5, 0 0.1, 0. So this is for, what was your first variable? First variable was, yes, right, xp. This is s value. So this, the first column is your x values, this is your y values, and this is your p values. This first row corresponds to t equal to 0, second row corresponds to t equal to 1, and third row corresponds to t equal to 10. So if I want to extract a t equal to 1, what is the product concentration? Product is my last entry, right? So product is my last column. So in the last column, I take the middle value. That is this one. Last column, second row. So that is 0.0563. Okay, likewise, you have to extract the particular indexes. So if you see here, the first index was second row, third column. Likewise, you can extract the index and you will be getting the particular answers, what is given in the question. So let us, few people have given me the answers. So at concentration 1, which is basically this one, you will be getting 4.8122, 0.133, and 0.0563. Yes. Because, yeah, your all answers are right. And for t equal to 10, you will be getting 4.4766, 0.3664, and 0.1570. Yeah, very good. Okay, I want everybody to solve answers like this. So let us move on to the second question. So here also you have like three variables, y1, y2, and y3. Okay, so initial values are also given, and you have to solve the interval. Time interval is given, initial conditions are given, and what else? Yeah, you have to plot it and also specify what is the value at t equal to 5 and t equal to 10. So this is 0, 5, 10. This should be your time span. Okay, so I'll give you a few minutes and then we'll discuss the answer. Any answers? Yeah, I'll give you 1 or 2 minutes. Yeah. So let's discuss the answer. So let me share Matlab quickly. So here the T span is, I need for 0, 10, 5, 10 was 12 asked in the question. Just a second, let me just see. No, 12 was not asked in the, okay. So its interval is 0 to 12 and additionally you have 5 and 10. Okay. So you have T span 0, 5, 10, 12. And initial value is 0, 1, 1, and my function is written like this. Okay, this is my function f dot m. So f dot m, it takes in 3 variables. If you want, you can separately extract, okay, v1, v2, v3. Since equations are very simple, I have taken this is v2, v3, v2 multiplied by v3. This is minus v1, v3, and this is minus 0.51 v1, v2. These are my 3 functions. It comes as a column vector. Now that is taken outside to ODE 45. I'll get T and Y for this particular 4 time spans. I'll get what is the Y value each. Now for plotting, they've asked us to plot all the solutions together. So I'll just plot T and Y. You will get 4 lines, each corresponding to, sorry, you will be getting 3 lines, each corresponding to Y1, Y2, Y3 respectively. Now I'll run this code. So this is how your plot will look like. Okay, you have 4 lines. The blue line is for Y1, your red is Y2, and the yellow is Y3. And these are the values. For t equal to 0, this is the value, initial guess. That is 0, 1, 1. For t equal to 5, you have the second row. which is 0 minus 0.9114 minus 4.108 and 0.7591. Yeah, you've got the right answer, Vikash. And for the t equal to 10, you have 0.8775 minus 4.786 and 0.7792, this row. Okay. I hope now it's clear how to solve questions. Yeah, this answer is also right. So, do you have any questions? Any doubts? Okay. Since nobody is asking any doubts, I'll just move on to the next question. Yeah. So this is a second order equation. You will have to convert this into two first order equations and then solve. All the constants are given to you. Omega is equal to 0.5. Initial conditions are given. X is equal to 0 and dx by dt is equal to 0 for time t equal to 0. Okay, you have to give the solution for t equal to 2 and t equal to 5. So I'll give you a few minutes and then we'll discuss the answer. Okay, I've got some solutions, so let's try to do this. So first, how will the equation look like? Just a second. So how will the equation look like? Here you have uh, that dx by dt, let me call it as v. So it is d square x by dt square is v, it's v dash, right? Yeah, it's v dash or okay, or dv by dt. Let it be. So now replace this here in this equation. In this equation, it will be dv by dt plus 3v, right? Plus 2x plus 3 sine omega t equal to 0. Bring everything to the other side. So this will become equal to, this whole thing will be minus. Okay. So the first equation is this, dx by dt is equal to v, and next equation is dv by dt is equal to minus of 3v plus 2x plus 3 sine omega t. The minus is for the whole thing. Okay. So this is what the equation looks like. Now going on to Matlab. So my initial value is 5 comma 0 for x and v. Now my initial time is 0. My t end I'm giving 2, 5. So my entire t span will look as 0, 2, 5. Now my sine fund is the function that I am writing. We'll take t and v as input. My first v is nothing but x variable and second v is my v variable. Omega I'm writing it as 0.5. My first function is dx by dt is equal to v. Second function is minus of 3 sine omega t plus 3v plus 2x. And this will be a column vector that is sent as an output. Now the question is I have to show what is x1 and x2. So x1 and x2 is, so I'll just run this here, clear CLC. So you can see YSolve is having 2 columns and 3 rows. So first column is corresponding to X, second column is corresponding to Y. And they have asked us to print at T equal to 2. That is, it is the second row, first column. So that is 2, 1. Okay. So that is why the value is 0.73196. Next at T equal to 5X, that is the third row, first column. That is why it is given 3, comma 1, third row, first column. You get the value as minus 1.211. Let me just check. Yeah, 0.732 and minus 2.110. Yes, you've got the right answer again. Anybody else having any doubts? Okay. If no doubts, let me move on to the next question. I'll give you a few minutes for that also. Its plot is cross. Okay, let me see that. Okay, let me just plot it and see once. Plot t sol, comma y sol, line. Yeah, is this how you're getting the plot? Yeah, okay, good. Now we'll go on to the next question. Here, you have to solve it using ODE 15S. The question is to plot the function. So after plotting, just let me know in the chat box. Just tell me that you've plotted, okay? Then we'll discuss. think, sorry, I forgot to switch on the recording previously. So, am I sharing? Yeah, of course. So, this is the problem. As I said earlier, we start with a t-span of 0 to 20. That could be any other time interval also. Initially, I'm taking A0 to be 1 and B and C to be 0, 0. And this is my ODE 15 years. My t-span I'm taking 0, 50, and this is my function rates. I'll just open what rates is. So rates takes in t and y values, and initially I'm declaring all to be zeros. It could be, if even if you don't declare it also, it's fine. And then this is my first function, minus 0.1 y1. This is my second function and third function. If you want to make it simpler, you can just write three variables where it extracts y1, y2, and y3. Okay, that is also completely fine. And this column vector goes as an output here. Now here, this is my initial guess, 1, 0, 0. And I'll plot this together right now. Just give me a second. Clear. CLC. Let me run the code. This is the kind of behavior you will be getting. So this is reaction in series. So this behavior, you would have seen it in in your chemistry problems also. That is, initially your A value will keep, so this is A. Okay, A value, it is 1. It keeps on decreasing because some of your A is getting converted into B and C. Now B is what you see in this red curve. B is the intermediate reactant. So what happens is, initially as A starts converting, your B concentration will keep increasing. But it will reach a maximum and then decrease. Why? Because after a stage, B is converting into C. Okay, so there is an equilibrium position where you will get a maximum B. After that, B will keep reducing because it started converting into C. Now you will see C first, it will be a slow progress, and finally you will see you will have more C compared to A and B. So your A and B concentration has come down. At the end of the reaction, you will have more of C here because A is converting into B and B is converting into C. So have you understood why this behavior is? Yeah. So in that case, let's move on to the next question. This is the fifth problem. You have two equations in dy by dt and dx by dt. Two initial values 0.03 and 1. And now you have to t-span is given as 0 to 1. Okay. Now you have to find the concentration of cell mass. So which is a cell mass? So y corresponds to the cell mass and x corresponds to the penicillin concentration. We have to find what is the value of y at t equal to 1. That is basically at the end of your time span, what is the time? That is what you need to find out. I'll give you 2-3 minutes and then we'll discuss the answer. Once you've got the answer, please put your answer in the chat box, okay? And then we'll discuss. Okay, so let me discuss the answer. So we have this question here. So initial value is 0.03 and 0, and time span is from 0, 1. You're using ODE 15 years or whichever ODE you use, it is fine. And this is the function. I will show you the function. You have the variable 0.0 A and R, okay? And then, sorry, not this one. Yeah, this one. You have the, sorry for showing you the wrong function. So ferment fund, T and Y. In Y, it extracts small letter y and small letter x. And this is how your function looks like. This is your first function, minus 13.1y minus 13.94y square. And the other function is 1.71y. So you have your two y's here. And then your t span is from 0 to 1. Your initial value is 0.03 and 0. You try to run this and then we'll also plot it. Okay, but the question is to get the concentration as T equal to 1. How do you find that? So this is the plot you will be getting. Your cell mass keeps on increasing and then reaches saturation, and your penicillin growth, it keeps on growing. Okay, so now you have to get, the question was to find what? The cell mass, right? Yeah, question was to find the cell mass, which is your second variable. So you have to look at the second column. So your TS is like this. So TS is this and YS is two columns like this. Your first column is for the penicillin and the second column is for the cell mass. So we go to the second column and the last row. Since you don't know the last row, you can use the keyword end. Okay. So that is, you'll be getting num to str. You'll be printing the solution. The end row, you don't know the number, so you just type end. It will automatically take the last row and the first column. First column, just a second. The cell mass is the first column or the next column? Yeah, sorry. Here dy by dt, this is the first column. Here the order of variable is yx, not xy. Okay, so this is the first column and this will be the second column. So basically you need the second column, last row. And the answer you'll be getting it as, let me run this again. You'll be getting 0.93965. Yeah. And the other answer will be, if you want to get what is a penicillin value, penicillin value will be 1.1846. Yeah. So I hope you have got the answer. Yeah, your answer is right. So that's it for today's questions. I hope the concepts are clear. In case you have any doubts, you can ask me right now, or else I'll be ending the session today and we'll meet the next Friday, the same time, 6 to 8 p.m. I'll be also sharing the recordings in the website. So any further questions? Okay. So thank you so much and we'll meet next week. Okay. Thank you so much for being active in the class also, Vikash. Okay. We'll meet in the next class then.